Now that we know that the determinant of a product is the product of the determinants, let's use that to calculate a couple more facts about determinants. So let's show that A is invertible if and only if the determinant of A isn't 0, and let's also express the determinant of the inverse in terms of the determinant of the original. All right, so to show that A is invertible if and only if the determinant of A isn't 0, let's suppose that A is invertible. So we'll suppose A is invertible. Well, if A is invertible, then the reduced row echelon form of A is the identity, right? The reduced row echelon form of an invertible matrix is always the identity. Well, in that case, we can write the determinant of A is, it's the determinant of the product of the elementary matrices that reduce A, or their inverses actually, okay, times the reduced row echelon form, but right, that's the identity in this case. Since the determinant of this product of matrices is the product of the determinants, we get the determinant of E1 times so on up to the determinant of EK. But the thing is, if you look at all of the determinants of the elementary matrices, they're all non-zero. And so here we have a big product of non-zero numbers, and so the product isn't 0 either. So if A is invertible, then its determinant is non-zero. Okay, well, let's go the other way. If the determinant of A isn't 0, well, we've seen that the determinant of A is the determinant of all of these elementary matrices times the determinant of the reduced row echelon form. So here we know that the determinant of the reduced row these determinants of the elementary matrices, none of these are 0. So this big product in front is 0, or is not 0. So for the determinant of A to be 0, right, if this one isn't 0, this one can't be 0 either. So this determinant is also non-zero. Well, the only n by n reduced row echelon form with the non-zero determinant is the identity. So the reduced row echelon form has to be the identity, and in that case, A has to be invertible. So A is invertible. All right. So now that we know that having a non-zero determinant is the same thing as being invertible, let's see if we can figure out the determinant of an inverse. Well, the determinant of A inverse, well, let's do it this way. What is it that characterizes an inverse matrix? It's that A inverse times A has to be the identity. Well, let's take the determinant on both sides. This says that the determinant of A inverse of A, or A inverse times A, has to be the determinant of the identity. But we know the determinant of the identity, it's 1. What about the determinant of A inverse times A? Well, the determinant of A inverse times A is the determinant of A inverse times the determinant of A, right? Because the determinant of a product is a product of the determinants. But then we can solve for the determinant of A inverse. The determinant of A inverse is 1 over the determinant of A, which kind of makes sense, right? What this says is that the determinant of A inverse is the inverse of the determinant of A, which is kind of what you would hope, but is actually true. You can see this determinant has a lot of nice properties that are pretty surprising. For a final trick, let's find the determinant of the transpose of a matrix, right? We might expect, given everything else we've figured out about the determinant, that there's some nice way of expressing the determinant of a transpose in terms of the determinant of the original. Okay, well, right, we only have a few tricks, so let's try writing A as a product of elementary matrices times a reduced row echelon form. Okay. There are two cases. So first case is that First case is that R is the identity. So in this case, A is just E1 up through EK. Well, then what is A transpose? Well, A transpose, one thing about the transpose that we figured out is that the transpose of a product is the product of the transposes, but in the other order. So A transpose is E sub K transpose times dot 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 up through E sub 1 transpose. And the thing about elementary matrices is that if you take the transpose of an elementary matrix, you get another elementary matrix. Okay, so the determinant of A transpose is the determinant of E sub K transpose times the determinant of the next one, and so on, all the way down to the determinant of E sub K transpose, sorry, E sub 1 transpose. Okay, so the determinant, so if you have any elementary matrix, right, if it's a permutation matrix, like this, a matrix that switches rows, the transpose is the same thing. If you have a matrix that multiplies a row by a constant, like this, the transpose is the same thing. And if you have a matrix that adds a multiple of a row to another row, then the transpose is like this. It adds, instead of adding a multiple to a row below it, it adds a multiple to a row above it. So, but the key thing is these are still elementary matrices, and each of these has the same determinant as its transpose. So the determinant of, no matter what kind of elementary matrix E sub K is, the determinant of its transpose is the same as the determinant of E sub K. And this goes for all of them, so that's true all the way down to the determinant of E sub 1. All right, well, on this line we have real multiplication, so we can rearrange this if we want. We can write this as determinant of E sub 1, and so on, times the determinant of E sub K. But then we can do the use the product property for determinants backwards and write this as the determinant of E sub 1 through E sub K, but that's just A. So what we found is that the determinant of A transpose is equal to the determinant of A. This is pretty surprising. Oh, I guess we need to prove it for the case where the reduced row echelon form isn't 0. Okay, so second case, reduced row echelon form has a row of zeros. So another way to say this, because R is n by n, another way to say this is that the rank of R is less than n, right? Well, the rank of R and the rank of A are the same thing, so these are equal. Okay, but the rank of these things is the dimension of the row space. But we've seen that the dimension of the row space is the same as the dimension of the column space of A, but that's that's the same as, right, the column space of A is the span of the columns, but that's the same as the span of the rows of A transpose, because the rows of A transpose are the columns of A. And the dimension of the row space of A transform, or A transpose, that's the rank of A transpose. Okay, so what this shows, right, looking at this big chain of equalities, is that the rank of A transpose is less than n. And A is n by n. This means that A transpose is not invertible. Any invertible matrix has full rank. So since A transpose isn't full rank, it's not invertible. And that means that the determinant of A transpose has to be 0. But by the same token, the determinant of A also has to be 0. Right? Exactly the same argument, right? Here we have the rank of A is less than n, so A is not invertible. And so the determinant of A also has to be 0. So either way, right, whether the reduced row echelon form of A is the identity or not the identity, we've shown that the determinant of the transpose is equal to the determinant of the original matrix. This is sort of interesting in its own right, but it actually has a really important consequence, which is that we can expand the determinant of A along any row, which we already knew, or any row of A transpose, right? Because the determinant of A and the determinant of A transpose are equal. So we can expand along a row of A, or we can expand along a row of A transpose. But here's what I'm getting at. A row of A transpose is a column of A. So we can expand a determinant along any row of A or along any column of A, which is really a big surprise. So let's just look at an example. How about a 2x2 example? -3, 4, 7, I don't know, 6. Why not? So if we expand this along, actually I guess it better be 3x3 at least. So let me pick smaller numbers. How about 1, 2, -1, 3, 0. Let's give ourselves a 0. 1, 0, 4, -3. Okay, well let's expand along the second row. If we expand along the second row, we get, let's see, -3 times, and then I need to determine it here, so -6 plus 4. -6 plus 4 is -2. Okay, so that's a minus and then a plus on this one, so plus 0 times whatever, -1 here times these guys, so 4 minus 0, so 4. So 6 minus 4, that's 2. Okay, now let's expand along the first column. Now when you expand along a column, the pattern of pluses and minuses are the same, right? The signs coming out of the cofactor is the same, so still it's plus, minus, plus, minus, plus, minus, plus, minus, plus. Okay, so when we go down the first column, we're going to start with the plus 1 from this entry, and then times my little cross of determinant here, so 1 times -4, and then a -3 times -6 plus 4, so that's -2, and then plus 0 times whatever. So -4 plus 6, that's 2. You see, we get the same thing whether it's along a row or a column. So this lets you, this flexibility of being able to expand a determinant along any row or column really gives you some flexibility to choose the most convenient calculation. So if you see any row or column with a lot of zeros, take that one.